Okay. So today I want to speak about thermodynamics of stationary states, so which includes equilibrium and non-equilibrium, and especially of I want to speak about thermodynamic transformation in general for from a stationary state, non-equilibrium, to another one. You see, I mean, there is a certain this is something that I started already more than 1 year ago. There were works by Christian Maes and by our group in Rome, and there is a certain consensus that quasi-static transformations are the best both in equilibrium and non-equilibrium, so very slow transformations. However, if you look at thermodynamic textbooks, you find that what is a quasi-static transformation is described only in words. There is no mathematics behind, and so I will discuss how you can discuss mathematically this. So these are my co-authors with whom we have developed an approach to diffusing, to stationary states of diffusing systems in the last 10 years. And so that is what I, let me see. Okay, this will be the content. There will be some preliminaries, point 0, 1, and 2 to set up the language, but I will be very sketchy on that. And then the real, the main point will be to discuss thermodynamic transformations. Okay, so well, let's go very quickly to what has been our approach in the last that we have developed, and which is now, it has a name in the within the community. It's called macroscopic fluctuation theory, and it has been developed not only with our contribution, but from our point of view. I mean, important contributions have come, for example, from Bernard Derrida in Paris, who has used this point of view to derive a certain number of results. And then complementary approaches have been by Christian Maes. And so the first point that you have to discuss when you go out of equilibrium is the fact that if you want to make a theory, a thermodynamic theory out of equilibrium, whether you can define thermodynamic functionals like thermodynamic potentials, like free energy typically, or entropy, or something else. And so that was the first point to discuss. And and then you see in equilibrium you have essentially the probability distribution for free, which is Gibbs rule, e to the minus beta h. And but out of equilibrium you cannot avoid. So that is the we have with these people we have developed a point of view, and which has been quite useful in many situations. Of course, when you go out of equilibrium, the richness of situation that you can consider is so wide that you have to concentrate and select some. And we concentrated on diffusive systems, under which are actually the most discussed also in all thermodynamic texts on non-equilibrium thermodynamics. So the starting point, I mean, this was not the historical real way, but for us. But logically, I think what we have done is to define for the first problem, which was to define non-equilibrium functionals, is a generalization of Einstein's theory of large fluctuations. Actually, Einstein's paper, which is of 1910, is not so well known because there is a beautiful introduction, which I think is the first example of large fluctuation theory in physics that I know. But then the rest of the paper, which was devoted to critical phenomena, is essentially wrong. So it was strongly criticized by Onst and Zernike, who proposed the first theory of critical opalescence. So it's not so well known, but the beginning, the introduction of this paper is really remarkable. So I use the notation of Landau-Lifshitz, which is the only textbook where you can find this theory. So the question was, suppose you have a macroscopic fluctuation. So you have a system, you have a system, a macroscopic system, and part of it, the macroscopic part of it, goes out of equilibrium, and you have a fluctuation. And and then you see what Einstein did was to reverse the Boltzmann relationship between entropy and probability. He said, I mean, I will never be able to calculate the probabilities, so I will. On the other hand, we can put our hands on entropy thermodynamically, so I will use this to define the probability. And so he wrote essentially this formula, where this quantity, you see, is something which depends at T0 and P0 are the environment parameters, so are the equilibrium parameters of the large system. And you see that this quantity is a mixed quantities, which depends both on the system and the environment. And actually it has a name. It is called availability, but it's a word that is unknown to physicists. It has been always used by engineers. And it's the minimal work that you can, that you have to spend to create such a fluctuation in a reversible way. So, and it is called also in the literature exergy, but it's only in the engineering. And the only thermodynamic treatise where this is discussed and the name is given is Pippard, book on thermodynamics, which is a very beautiful introduction to thermodynamics. So, so the idea was to, let's try to define out of equilibrium what is this minimal in minimum in an out of equilibrium situation, so in a stationary state. And so, and of course, as you can expect, the mixing of environment variables and system variables is much more complicated if you are when you are in a non-equilibrium situation. Okay, so so the typical setting we want to discuss is that we have a system and where which is in contact with several reservoirs, and so you have currents of different kinds going through the system, which may be matter, electricity, heat. So the non-equilibrium stationary state is characterized by currents flowing through the system. And we make a certain number of assumptions, which are those that you find in thermodynamic books. But actually, we have been guided always by models. So these are called lattice gases, for which you can develop a rigorous theory. And so actually, if you think of a wide class of lattice gases, these are not assumptions, but are proved statements. And the point, there are essentially one point that you have to prove, that in order to have hydrodynamics, that you reach at the macroscopic level some local equilibrium. So this means that the system has enough ergodic properties that it goes locally to equilibrium much quicker than the whole system. So and the long time behavior will be determined by the hydrodynamic modes. So there is a separation of scales. I mean, even at the macroscopic level. So we have we have continuity equations, and we have a constitutive equation for the current. So we have a diffusion part, and if you have an external field, and you have the mobility, and then we have, and this will play a very important role, what is usually called the Einstein relationship, which connects and that is due to the local equilibrium, the diffusion coefficient locally with the mobility and the second derivative of the specific equilibrium free energy. So this locally this relation holds, and this for these models it can be proved. In general, the field will be assumed. If you want to consider thermodynamic transformation, you have to assume that it is time dependent. And then you have, of course, boundary conditions, and this can be expressed in the following way, which relate the chemical potential at the boundaries with the equilibrium free energies, and so this determines the. And you see, also the boundary conditions will be assumed to be time dependent. So this is the situation we want to consider. So the typical question you may ask about thermodynamic variables is that what is the probability that, for example, you are in a stationary state, first some initial state is created by a fluctuation, and then this follows an arbitrary trajectory. So you are interested in the probability of quantities like this. Besides the usual thermodynamic variables, you have currents now. Currents are more complicated objects because they depend explicitly on time in their definition. Okay, so now rate fluctuation, so that is what I explained, what was the logic. So everything in this theory, as we have realized after a certain point, depends on a unique formula. On a unique formula which describes the probability of having a certain trajectory for the thermodynamic variables and for the current. And it's a formula for the joint fluctuations of this. This formula is a very intuitive meaning, but I mean, it is proved so you see, this is the exponent, so it's the sum of two terms, so the probability is the product of two factors. Now, the first one describes the probability of having the initial condition, while the second one describes the cost of having a profile, a current profile, but I mean, the thermodynamic variables has always to satisfy the continuity equation. And if you look at the form of this functional, you see, think of the power dissipated by an electric circuit. It is just the resistance times the square of the current, and this is exactly the form of this cost function. So the inverse of the mobility is the resistance, and this is the difference between the typical, so hydrodynamic current and the fluctuation. So it's just the form of a resistance times the square of the extra current that you have to. And everything follows from this formula. Oh, yes, you are right. I didn't mention it because it will never come into calculation, but the small parameter is typically a ratio. Is something, this epsilon to the minus the dimension of the system is essentially the number of degrees of freedom of the system. So it's typically the ratio of a macroscopic distance to a microscopic distance, like could be the Freeman path or something like this. but it never comes in the calculation. I mean, our aim is our interest is essentially in this exponent to define analog of this minimal work which appears in the Einstein formula. So, so as I said, everything follows from this formula, and actually it follows by rather general arguments, which are essentially time reversal arguments. You know, I mean, once you are out of equilibrium, time reversal is not anymore satisfied, but still you can define a time reversed system, which physically means the following, that acting from the outside, you can reverse every trajectory of the system. I mean, we are able to drive heat from lower temperature to higher temperature. So this is a very general assumption. And so the time reversed process is defined in this way. So the probabilities, I mean, the mu is the invariant measure, so the stationary ensemble, and the probability of the first process is equal to the probability of the time reversed process for the time reversed trajectories. Now, at the level of large deviation, this implies that the time A means adjoint, because the time reversed process is generated by the adjoint generator with respect to the invariant measure. So now, what is dense of consequence is this relationship. And from this relationship, you get that our analog of this, actually it is the interpretation, as we shall see, is again of minimal work. The analog of obeys in function space a Hamilton-Jacobi equation, which corresponds to this quadratic Hamiltonian. So, and this equation is very useful for many purposes, including perturbation theory around a stationary state. Okay. So, and from this equation, it follows that
chi is positive definite.
Chi is positive definite, yes. Now, from this Hamilton-Jacobi equation, it follows that you can write the hydrodynamics of the first process and the hydrodynamics of the time reversed process in the following way. You have a part, so you see, you can identify, just comparing with the equilibrium case, you can identify the gradient of the derivative of this large deviation functional, which is called quasi-potential, by the way. With the thermodynamic force, and then there will be another part which has different transformation properties under time reversal, and the two parts are orthogonal. This is just a consequence of the previous equation, and actually this depends on an orthogonal decomposition of the current, in which you can define an even part under time reversal and the not part under time reversal. The even part is just what appears here, and is connected with the time with the derivative of this large deviation functional. And the two currents are orthogonal in this sense. These brackets mean integration over space. So this orthogonality depends on integration over space. Okay, you should not be surprised by this. Because take the example of an electron moving in a viscous medium, as you find in the book of Ashcroft-Mervyn, for example. So in a magnetic field you have this term, and this is the dissipative part, and you see that the two terms are orthogonal, and in fact the time reversed equation is this one. So only this part changes sign. Now this so this is a generalization to any non-equilibrium state, and you have a kind of duality principle. Like, for example, in the Hall effect, you have that magnetic field produces a different in potential, and here you have the boundary conditions, non-symmetric boundary condition, produce a term which has the same transformation properties of a magnetic term. Okay. So, well, this is another example. There are several predictions which follow from this approach. I just list them. Generically, you have non-equilibrium long-range correlations, which is an experimental fact. You have non-equilibrium phase transition impossible in equilibrium. Maybe I spend one word. You have dynamical phase transition in current fluctuation, and you have certain universality relation for moments in current fluctuation. This was derived in particular by Derrida. Well, just by non-equilibrium phase transition, which is not possible in equilibrium. You see, the free energy is convex in equilibrium, but non-equilibrium you may have a situation of this kind. Okay, so let me skip all these things. What are these non-equilibrium? Oh, this can happen also in non-equilibrium and equilibrium current fluctuations, in which you have phase transitions in which you break spontaneously time translational invariance. You have a situation, for example, in which think of a ring where there is a system, a one-dimensional, then a fluctuation of current, if a small fluctuation, the system moves, rigidly. But for large fluctuation, you get a peak, a traveling wave, which, so this is a typical general phenomenon which is predicted by this theory. And this has been seen so let me come to the real subject of this. I mean, maybe I spent too much time on that. Okay. So, so I start with the energy balance that you have in a thermodynamic transformation. So, so the total work or total heat, here in purely diffusive system I don't distinguish between the two. So the total work is given by two terms. One is the work done by the external field, and the other one is what is provided by the reservoirs. So it contains the interaction of the current with the chemical potential. So this is the... Now this first term can be easily transformed using the Einstein relationship. And then you find that this is equal to the variation of the equilibrium free energy, but calculated on the profile of the thermodynamic variable which is given by the out of equilibrium conditions. And then you have a purely dissipative term. This can have any sign. A purely dissipative term, which is again of the form of dissipation of a current, like in an electrical circuit. For this, you get immediately, of course, the since this is positive, Clausius type inequality. And I think the second law is actually hidden in the Einstein relation. Now, since these two terms, these two currents are orthogonal, this actually, the dissipative part is actually the sum of two positive parts. And, well, you can immediately understand what is the meaning of the odd part under time reversal. You see, if you are in a stationary state, this is a minimum of the bar deviation functional. So this part is 0. And so you see that is the stationary current coincide with this antisymmetric part. And in fact, this is the dissipation that you have to spend in order to keep the system out of equilibrium. So they have a precise physical meaning. And then the thermodynamic interpretation of the quasi-potential consider, actually this is exactly the same transformation which is considered by Pippard for equilibrium. So you have some boundary condition, non-equilibrium, then you change them suddenly, and then the system relaxes to the new situation. And so this is, and then you see, you find that you can make explicit the the contribution to the dissipation of the symmetric part, and you find that this is exactly the difference in this quasi-potential. So, so this describes the work done by the thermodynamic forces, exactly like in equilibrium. And then you have this additional term, now which we have already interpreted. Now the point is that if you keep the system out of equilibrium, then when t goes to infinity, I mean, you have to spend an infinite amount of energy, because so this term actually goes to infinity. So if you wanted to make, I mean, verify the energy conservation, I mean, here you are in trouble. So following a suggestion which was made about 15 years ago by a Japanese physicist, and Ono and Panikuni, they were at the University of Illinois, we defined, and because this is natural in our scheme, normalized work by subtracting this part which is necessary to keep the system out of equilibrium. And a different definition was given by Christian Maes and Nitochny, which is based on an entirely different idea of making a comparison with the system in which in the stationary state you have minimal entropy production. I think I'm correct. If I'm wrong, you correct me. And it leads exactly again to the same clauses inequality. So this is, well, I will skip the comparison between the two, but I don't know whether Christian will speak about it. No, not this time. Okay. But I believe the comparison we did was correct because we published. Now, however, I mean, let's say 1 year ago I was very enthusiastic about this renormalized work for this. But then, I mean, this is not something that is easy to measure, because it depends, you have to make explicitly this separation. And so you have to calculate this large deviation functional and so on and so forth. On the other hand, once you have subtracted the work you have to do to keep the system out of equilibrium, you are left, I mean, you give up arguing about, because any transformation actually lasts for a finite time, long but finite time. Long, I mean long with respect to the relaxation times of the system, and and it's not really perfectly quasi-static. So this is a paper in preparation. You see, we have this identity, which were the one I started from, and so the idea is that you take a finite time, very large, and you expand around infinity. It's something like what you do to study adiabatic limits. And so we expand both sides of this identity, okay, thank you, in essentially in powers of 1 over t. So to do it in a mathematically clean way, you introduce protocols, which are the external driving of the transformation. You introduce a parameter, tau, which in the end you will send to infinity, and you define this rho tau and j tau as the solution of the hydrodynamic equation, but including this parameter. This is the usual current. And by a bar, I mean the unique stationary solution of the hydrodynamics. Okay. Now, if you make a change of variable, you can actually make explicit the dependent on tau, and these are the solutions of those equations before. And then you have, this is the dissipative part. Now you begin to do the expansion in powers of 1 over 2. So you will have the stationary solution, and then you have first correction, and so on, and the same for the currents. And this can be calculated, this first coefficient can be calculated by expanding the hydrodynamics, and and these are the equation obeyed by R, and so it's kind of Poisson equation for R. And then, for example, at the order 0, so you find first that the divergent terms cancel exactly on the two sides of this equation, and then you have that the difference in free energy must be equal to the work done by these first order corrections, and so these are the terms. To understand a little bit more this relationship, let's consider the case of you go from an equilibrium state to another equilibrium state. Then in such a situation, since you go through, if you go through equilibrium states, the intermediate states are all equilibrium states, this part does not contribute. And I put of course, the external field equal to 0. And however, if you go through non-equilibrium intermediate states, even if the initial and end state are of the of equilibrium, this term contributes. And since this difference is finite, then you see that the work is divided into so the contribution of the reservoirs and of the system itself have to readjust together in order to produce exactly the same variation of free energy. So you see, I think this provides a rather detailed description of what people mean by a quasi-static transformation, and you are able to locate in terms, because as Landau Lifshitz said, I mean, to move the system you have to bring it a little bit out of equilibrium, otherwise you don't move it. And this scheme allows you to calculate explicitly. These formulas, in simple cases, we have been able to verify they are correct. And there are cases where you can calculate everything explicitly by solving those equations. So, well, even the renormalized work can be, you can calculate the first correction, which is a positive definite term, which is related now to the large deviation functional, as you can expect. And this positive term, you can use this expression to optimize with respect to the protocol of the transformation. The last thing I will only think I mentioned, no, I will not discuss dissipation. I just discussed the, you know, if, I mean, one is not able to define a thermodynamic non-equilibrium entropy, but the Shannon entropy, once you have an ensemble, is well defined. And in fact, you find that the large deviation functional is just the relative entropy of the initial state with respect to the final one, or vice versa. Now, I don't remember. Anyway, you have also this interpretation of the large. So I think that is, I guess I can stop here. Well, this is the argument. Well, the summary is, I mean, is what I think it's short enough. I mean, I think now we are trying to use, but I mean, this expansion looks interesting because it gives you a set of identities in the energy conservation that you actually can verify experimentally. So in this sense, I think this expansion is useful. Thank you.
Comments or questions?
In the initial slide, you say that you can use macroscopic fluctuation theory phenomenologically. And
Yes.
then you say that it's difficult to use because actually you would need to have computed the.
Well, I mean, no, I say that it can be used phenomenologically because the only parameters entering are the diffusion coefficient and the mobility, which are measurable quantities. Then, of course, you have to solve, for example, this Hamilton-Jacobi equation, which in general you can do it exactly only in very few cases. But you can you can make a perturbation theory with respect to the stationary state. And in this case, you are able to solve it. And this is a step beyond Onsager. Onsager did this theory in equilibrium, near equilibrium, so he didn't have to define new thermodynamic functionals. But here you can make the expansion around any. So the point where we go really beyond Onsager is that there is no restriction on the boundary conditions. So in this sense you can have a far from equilibrium state, and you can expand down around this equilibrium state, non-equilibrium state.
Other comments?
You cannot put inertial term in this diffusion thing. I mean, go to hydrodynamic equation.
I didn't understand the question.
So you have diffusion,
Yes,
but no inertial term.
exactly.
Not
Yes, yes,
The-
exactly. Yes.
That's
Of course, you can have several conservation laws. For example, an example with two conservation laws was discussed by Cédric Bernardin, and it works. The scheme works. Of course, I mean, everything is more difficult than equilibrium. You have to solve certain variational problems in which, and you see, this non-equilibrium minimal work is generically a non-local quantity. This means that if you want to reverse the trajectory, you have to act on the system in a correlated way in different points. But that seems to me, I mean, from another example that I'm not been able to discuss today, I think my idea is that really all this is imposed by the time reversibility condition, by the fact that you have
You mentioned this theme of non-equilibrium phase transitions. Where would you suggest to look at in nature or an experiment to see non-equilibrium phase transitions that would be easiest to analyze within that framework?
Look, I mean, this the transitions, the phase transition in current fluctuation were then discovered. I mean, not discovered. They were shown to exist by simulation by Hurtado and Garrido, I believe, in Spain. And now this is more difficult to simulate. So I think the first step would be try to. I mean, we proved that this transition exists in the weakly asymmetric.
Are there somehow obvious non-equilibrium phase transitions around us that are awaiting for such analysis that somehow are here and there and somehow have not been studied? Or, I mean, what should we have in mind in nature or an experiment for non-equilibrium phase transitions?
Well, for example, yes, I did discuss. Okay, I mean, this quasi-potential, this minimal work, is the solution of a variational principle because you have this Hamilton-Jacobi equation. And now, what usually happens is generically you have only one minimum in this variational principle. This phase transition arises when you have more than one minimum in the variational principle. And so this is the I mean, in the finite dimensional case was discussed long ago by Graham and Tell, heuristically in finite dimensional case. But we were not able to find any real proof for the finite dimensional case, but somehow we succeeded to prove it rigorously for the weakly asymmetric simple exclusion process. And so it's connected with the existence of two minima in the variational principle. So this is it's really a bifurcation. Experimentally, you could reverse. You could take an active point of view in fluctuation. You don't have to wait for the age of the universe, but you try to find the optimal driving that generates the fluctuations. And at some point, you will find that there are two entirely different drivings that spend the same amount of energy to produce the fluctuation.
Thank you very much. I think that will teach you.